I'm listening to the room. There is an enthusiastic discussion over there.
Yeah.
But let me reconvene the session by just asking one thing, Philippe. Once it is possible to really continue the discussions in the afternoon, I mean, probably we could. Do you think it's reasonable to really still keep the schedule of stopping at 12:30, and then we would continue in the afternoon? Does this?
Yes, the thing is, this afternoon we'll have the talks.
Oh, that's right. That's right.
I'll try to rush. I really try to rush because the lecture tomorrow also is very good. I mean, it's a really new thing that I'm urged to show.
Okay.
To show up. And
yes.
I think that I drank too much coffee, so I might be speaking like really fast now. So.
Okay, but Philippe, don't forget that you are speaking to students. Okay. So.
Yeah, I do. I always keep remembering like this.
Okay, we don't put the delays, Philippe. I give the session to you. The floor is yours.
One thing first, and this is like as we call it in Brazil, jabá. I mean, this is a thing that we have like this new special issue now, and I will invite everyone to publish in this new special issue that we have like exploring new physics with deep learning in the area of collider gravitational waves experiment. Really long title, so everyone is invited to submit your papers and your findings on gravitational waves, on collider physics, and cosmology. Antonio can give like some can give some brief introduction and what one could expect.
So everything is written so in this website. So you have the description of what is the special issue going to be. But so the guest editor, it's me, Felipe, and Roman from Lund University, as you can see on the screen. And this is dedicated to this intersection between high energy physics, gravitational physics, and deep learning. So, this is just an announcement. This was just published today, and the submissions are until June next year. Actually, July. So end of June next year.
So yeah, please feel free. I mean, does it need to be on deep learning stuff? I mean, it can be anything that related to the field, and I will really appreciate your submissions, and we'll take care. We'll take really good care. Yeah. So let's keep going with our walkthrough, our speedrun, like this. I think that, okay, let me just close here, and I can, yes, we are going today with the Jupyter Lab stuff. I get used it, and I'm just like close this tab to make it a little bit bigger, and we are open the lecture for today. So far so good, we survived it. And yesterday, I mean, first thing, second things, it was like some of your people could not run my code because it was missing the noise. Okay, I updated the GitHub to put some noise data, at least like the smallest one. You go to Git, you go to the, let's see, the compact object, gravitational waves, and you see a new folder that's called noise data, and you can download some of the noise. The longer noises are on the Google Drive. I will put the link on the chat after the lecture, so you can go grab and download if you don't receive it by email. And I will ask to Alexander to send the email again. And you have like the images, the already generated images from you for the deep learning session, and for the noises if you want to generate your own images like this. Okay, so no worries. So far so good. We are going to right now finally build something useful with the data we generated. Okay, and I hope so to build the useful thing. So, I mean, to start at some point, and we should like at least the basic idea points like this. So what is a neural network? What are we going to build this? I'm talking a lot of this, and I didn't clarify enough on this. The neural network is based on the biological process, like the neurons that we have, and you give some signal, and the neuron will just like, okay, if the signal is above some threshold that I have, it will pass along. If it's below, it will not do nothing like this. This is like the main basic idea of neural network. And we have here, we can just like modern this kind of approach using this way that we have like the weights. The weights will be like how much your signal has to be evaluated by the unit, the neuron, to pass along. I mean, this will be like your weights, and your bias, you'll be like, it will not be passed if below this kind of threshold. If it's above this threshold, it will pass the signal. If it's below, it will not do nothing. This is like the main idea. And we can think this as like a kind of like a very, it can be huge or smaller circuit that we have these knobs and dials that we can like turn up the dials or switch on and off the knobs, and we have all of this. You can build like very, very complex circuits with these kind of things that you can, each time that you couple together this kind of knobs and dials, these in series, you can make like very, very complex decisions based on this, okay? The main idea, if I'm not too complicated to say, it was like we have like a series of knobs and dials coupled together, and depending on how you select this, how you turn on and off, or how strong your dial it is, it will make very, very complex decisions. Right? So this is one very simple way to think about this. And of course, this is like really, really old. These things is been around since the 1950s, 1940s, or something. And even earlier, people are discussing about, like Alan Turing was like discussing about this kind of circuits that we can put together and everything. However, we are in 2020, although it's not like a really great year so far, but okay, I mean, we have worse time, so we should at least try to use something that's like a kind of like a modern like this. These convolutional neural networks, they are like a modern-ish or something, which are like some sort of like a extension from these neural networks. These are called multi-layer perceptrons, and the convolutions, they are like the next step of this. So what this convolution does, it was like, okay, we have like a 2D images, and we go through each one of the pixels of the images. We go through this, and we make the convolution operation. Like the convolution operation is just like a matrix multiplication, like this. You have your filters that are the convolutional filters that you take that part of the image, as we see here in this animation below. You see here, you take like you take like a 3x3 of your images, constructing as a matrix, multiply by my filter. The filter will be like the thing that my dial, like say my dial and knob, multiply by this filter and create a new pixel of the image. This is a convolutional operator, right? So that means that when I say that this is a regularized multi-layer perception. This is like a more controllable way to do this. And before the use of the convolutions, it has like the ImageNet competitions. People are only using these kind of a multi-layer perceptrons, and they have like a really shitty results. They have a really, really bad results. So only using this, especially with this problem here that was called like a handwritten data set, a handwritten image. I think that was Ian Khan that first tried to use these convolution operators, and he got like a 99% of accuracy, and people would just go crazy and start to rush and use this kind of convolutional operator, convolutional neural networks like this. So One thing that we are discussing about this morning, and I updated this here, it was like, okay, this machine learns some things, this machine learns things from the data. What are the things they are learning? What are the things they are doing? And these convolutionals, they are doing this kind of imagery feature extraction, let's call it, let's say. Each layer of the neural network will be specialized on some sort of features like this. And as you see here, you have like this first layer, you have like this kind of filters. You can think these filters, you can think like these convolutional channels like this as an image. You can think like this. And this is a HasNet trained, and you pass the image to this, and you can actually grab the weights and bias. You can grab these filters and you plot as an image. And you can kind of like see what the neural network is learning. What are the features that are important for that kind of decision like this. Tomorrow we are going to explore a little bit more. But as you can see, like in the first layer, we have these channels, these convolutional channels. And you see some of the channels, they catch like brightness, variation. Another ones catch like the edge of this. And all of these features, it will be important for the neural network to make the decision, to make this. So this is, remember when I said that's like, okay, it is trying to catch up some features, some edges, something. So this is what I'm trying to say. Like, this is like, and if you go deeper and deeper like this, the neural net tends to be more specialized in some filters and more abstract like this. So you see here in the convolutional block 5, like you have like in the deeper layer here, you see this kind of very abstract things. Like, I mean, I can understand, but for the computer, it makes a lot of sense. So it starts to become like blurry. I mean, here we can understand why, but at the block 3, we don't have no idea what the neural net is doing. But for the neural net, it makes complete sense to look at this kind of abstract features. Which, if you're thinking about like this, it's kind of like our brain processing images. I mean, we evolved to process this kind of thing. That's why we tend to appreciate more images with like a different brightness or different gradients or something. Because during our evolution process, if we can see things a little bit more better with a little bit more definition during the dark, we survive it more. So this kind of the same kind of approach that we are doing here. And for me, it's really surprising that we are trying to mimic these kind of things. And we can even explore, we can try like to understand how our brain works by using these kind of things as well. There are like lots of people doing this kind of research on how neural networks learn things and how human beings learn things, and try to bring these together, like try to understand a little bit more together. And yes?
Who decides about this degree of abstraction?
Who decides this? The stochastic gradient descent. I mean, the training of the neural net is decided this kind of a feature. We are going to see in a moment what are the kind of decisions and who decides which are the filters or the regions which are the best one, like this.
But when we decide to work not for under our control, we can say we have 1, 2 layers or 3 layers or
yes.
20 layers.
Yes.
And that is related to this.
Yes, exactly.
Maybe for some problems, it's not necessary to go as deep as.
Yeah. Most of the time we don't need like to go so much deeper with this kind of makes so much abstract. I mean, as a matter of fact, I have a paper that we demonstrate that's like sometimes for some examples we just need 2 layers of a neural network, or even like 1 layer like this. Okay. So any other questions? We can proceed. I think I will not have time to do this, but yes. So to build our neural network is like it's really easy. I like to think about this like a kind of like a Lego. You are playing with Legos, Although I never played with Lego before, I mean, I was really poor, so I never have the opportunity to play with Legos, but I like to think about it as this way. That you have to build your data that you are going to feed to the neural network. Your data will consist of your images, I mean, the features, in the input, and the targets. And here in these nodes, each of one of these nodes, that you can be really creative. You can like put some activation functions different, lots of deeper layers or not deeper layers. You can do whatever you want on this kind. This is the main part of the thing that people spend a lot of time doing research and try to modify this kind of thing. And also the loss function. The loss function will help us to evaluate how well our neural network is performing, because it doesn't matter. You can feed the data, but you have like to compare with a ground truth. I mean, you have to know what you are feeding. When you are doing this kind of approach, it's called like supervised learning. You know your answers that you are giving, and you are asking for the neural net to perform the task that I want. So one thing that we were discussing this morning, it was like, okay, why these things work so well? Why these things are like can give like a superhuman predictions for some things that why this thing? Why? Because these things are rooted on the universal functional approximation. That's right. You can go on the mathematics, on the computer science, you have like this, and I can tell you that's like the universal functional approximation. As simple as I can put, it's like okay, there is some function in the universe that can give you the difference between if an image is a cat or is a dog. And the neural net will try to approximate as close as possible to this ground truth function. We don't know, but the neural net, by the training and by the tricks that we are going to give to the neural net, we will try to do this. Not only like to classify these things, but also if we have a problem that I'm working with one of Carlos Zeder's students, let's have like solve some partial differential equation, and we can build this. We can use this universal function approximation to try to solve this partial differential equation using this neural net, because we don't know for sure what are the exact solution, but we can build a really good function that approximate very, very well to the exact solution, and we can use this as well. So that is why this field worked with classify cats, dogs, gravitational waves. That's what this thing is, because this is rooted on this universal function approximation. Okay, so the main step, the first step here is to build our data, because build our data, we have like to give the images and give what the labels of the image is. If I not give this, we cannot compute the loss, and it will be kind of hard to train our neural network based on this kind of thing. So we are using supervised learning. There are unsupervised learning, and there are also semi-supervised learning. The unsupervised learning, you just give the data and ask for the neural net or ask for the algorithm to figure out yourself what are the classes of it. There are some cases that this works very, very well, surprisingly well, but still is a really new field of research, this unsupervised learning, which is, as a matter of fact, in the nature, what most you will find, it is unlabeled data. Unlabeled data is like, I have lots of phenomena, lots of things that you don't know how to label this, that you don't know how to classify, and it's quite expensive to do this kind of thing. So this supervised is like a kind of like an edge case that we can name things, that you can classify things, and we can use the ground truth. The unsupervised is the real state, is the real deal, but it's really, really hard to do this. And the semi-supervised, you can say, okay, I don't know everything, but I know these things. Can you try to generalize these things that I know to the things that I don't know, to the things that are unlabeled? Can you try to do this? And yes, these things can do this with some confidence level. This is another field that I'm really, really interested in. I'm trying like to try to bring this together. So, okay. So where we can start? We can have like the data, the predictions, and we have, as I said before, we have like the neural network, which consists of these dials and knobs like this. And depending on how we change the dials and knobs, it will give really good prediction for some image, but it will miss the other ones. So we are going to try to at least get like really good predictions in most of the images, most of the cases. Like, ideally, all of the cases, but one must think that's like the ideal case, and the real case is not like the straightforward path. So one way to try to find this kind of knobs and turns, dials and things is to use the loss function. The loss function here that I'm put is not the same one that we're going to use, but the idea it is, we have the weights and biases that this loss function will depend, it gives you a number. And you have like the ground truth, the targets of the ground truth here, and you have like the predictions for the neural net. If my ground truth and the neural net is 0, we have like a cost function from 0. We are going to try to minimize this cost function, this kind of thing. And then we're going to, by asking this to minimize this function, automatically we're going to change the weights and biases for my neural network to give me this best prediction as possible. So what we are essentially trying to do, here is the mean squared error. We are trying to get our predictions as close as possible to the ground truth. Are doing this. This is the main idea. Okay? But the thing is, for a very simple neural net, even like for a one layer neural net, depending how many that you have, the weights that you have, it becomes really, really complex. It becomes really, really fast and complex. The ideal case that we are like to think is like we have like this function that we want to minimize the cost. We have like this kind of a valley, and we are going to follow the minimal path of the valley. We are going to do this kind of a thing. This is the ideal case, but the real case is the thing that you see here in the right figure, like this. These are animation from a loss landscape. That's like from a HasNet. I think that is a HasNet 34, 101. I don't remember. But you can go on this website, this losslandscape.com. They have like lots of animations, and they plot this kind of a really beautiful thing. I mean, this is kind of like a mesmerizing. And you see here, I'm just changing one parameter of the neural net. That's called like the dropout parameter. And to see how the valley changed during the time when I'm changing this, this is a really big problem, because when I'm going to find the minimal position on this valley, we can end up in places that are not the global minimum, but the local minimum. And this will make a really difference from your prediction. I mean, if you try to find the global minimum, it'd be great, because you are not getting really good predictions on your training, on the image that are training, but it will be really good to predict that the image you never saw before. Because of course, we found some universal function that you can give the image, and the function will give you like a really good prediction for if the image belongs to one class or another, like this. And this is like a huge debate on the machine learning field. It's like try to find the global minimum for any kind of a data or any kind of thing. But sometimes the local minimum is good enough for us. Okay, so I mean, no worries, but a little bit worried about this kind of thing. And we also have some other tricks on the sleeves that we can like, if we fell into a local minimum, we can get up from this and find a lower local minimum, or try to get lucky and get like the global minimum for the function. Okay. So one way to try to find this is to use the gradient descent, like this. So the gradient descent, it will be like this. We have like the cost function that depends on the weights and biases, and we are going to compute the gradient on these weight and biases that we have. The gradient descent it will be like this. How much will you change my weight in each layer, in each kind of things? It will depend on the change of the cost function. We want to minimize this, and to find the minimal position, we compute the gradient on this kind of terms. The thing is, if you notice here, this is an average of all of this. So to compute the gradient descent efficiently, we have to compute the gradient for each one of the images that we are going to feed into the neural network, and store this, average all of them, and then proceed to the next step of the training, all of this. So this is very, very computer intensive for this, and is not efficient at all. I mean, you have like to do this. If you think about, okay, 100 images, you can do this. 200, okay, 1,000, it became a little bit more difficult. And think about like there are some data sets, they have like 20 million of images. So it will be impossible for you. I mean, you can compute this as long as you want, but you go to nowhere like this. And we have like to publish our papers, we have to defend our thesis, and nobody got time for that. So one idea that comes to help it was like, okay, I don't need to compute in all my data set, but I can sample some random images or some random data from my full data set, compute the gradient on this, which is feasible, like this, and evolve. I mean, pass to the next step and do the gradient descent. And this is called the stochastic gradient descent. It's stochastic because we are sample some random parts of our data, and you are computing the gradient on this random part. And this accelerates really, really well the gradient descent. So this was like the breakthrough on the deep learning. This makes possible to training machine learning models, and of course the GPU stuff. We have to do this. So, but the thing is, we always have like to balance this kind of thing, because ideally, if we could like feed all the data and compute the gradient, it would be great, but we cannot do this. But we can sample some of these, and depend on the sample that we call it like mini batches, depend on this, it will be like you have like a really representative of your data itself. You can like, if you train with a big batch, your gradient you train a little, it will be more faster to training, and you have like a more representative of your full data set from this, which is good for you. However, if you give like big batches, it will occupy a lot of your memory, of your computer memory. So you always have like to balance this kind of stuff. Another thing that it is the learning rate. The learning rate is this value eta here. It is like the size of the step that your computer gradient. Like how bigger you be your step in the loss landscape. If your step is too short, it will take a lot of time so you can find the minimum. If your step is too long, you might pass over, you might go over your minimum, and you'll be like back and forth on the minimum. You will never find this. So we always have like to compute like these two kind of let's say parameters that they have. They are really closely related to one. You always think about this, like this step and the representative of your batch. You just always have like this kind of balance of view. And by experience, these are the main contributors for your accuracy for your neural net. Of course, the architecture is the main guy on the state, but the learning rate and the batch size also plays are really important on the neural net side. So, questions? No questions on the chat or anything? Please raise your hand, interrupt me, make comments. So we can move on. Okay. This was a really like a very speedrun introduction on gradient descent and all of this kind of thing. But I would recommend for you to just have a look on this. I will put on the website a really good introduction on this kind of. That was, as a matter of fact, that was the place that I took this main of this idea. I forgot the website, but I'll put. I promise I'll put the on the Git and on the chat in this afternoon. Okay, so we can move on. We can start to build. I have 10 minutes, and I don't know if I'll be able. At least, can you give like a little bit more 10 minutes so we can finish this today? So we have. Yes.
No,
Nothing?
just to tell you that I think it would be okay. I mean, if you...
Okay. So let's go.
Okay.
So we have the data generated yesterday, and from FastAI, we have this really convenient class that called image data loaders. This image data loaders is specific to work with image. You also have like text data loader, you also have our data class, but these one are the ones that we're going to use. And we define this path here, this function, which will create an object path, which will point to where my data it is, okay? I can even listen, like I can even look at what are inside of this data for classification. When you are going to run on your machine, okay, and you are downloading my data, the folder that you are downloading that has the target, it's already with this name, but you can rename it, you can put on this. So usually what you're going to do, you download this notebook, put on a folder, you download the data, put on the same folder on this notebook it is, okay? So in this way, it will not give any crash error. On the Colab stuff, you have like to mount your Google Drive and you have to put both on the same folder, okay? Or you can put towards, you can put the full path to the Colab folder. I can show this tomorrow, and later if you can call me, we can set up a session and I can show very quickly how to do this. So in the image data loaders, we have this function that's called the from folder. This from folder is really, really convenient because I don't need to worry about to label the function. The label will be grabbed from the name of the folders. We have here, BG is my background, and SIG is my signal, okay? It also has, like in my folder, they create like these folder models. This is created by the FastAI when I'm going to save my models and everything. But the main folders that we have like is background and signal. You can rename it, these folders, and you automatically put the classes on this. So what this thing it's doing is go to this path, see it has two folders. The image is one folder is from one class that we're going to classify, and the image for the other folder is for the other class. Okay? So I create this data loader here, and I can use this function that called the show batch to show me the images that he's loaded. Okay. And he's pick a random batch and put me on the screen. This is a really good thing. This is a thing that I really like on the FastAI. When when I started to use FastAI with TensorFlow, one of my main difficulties in TensorFlow, it was like, how do I know if the images are correct? If they are loaded, the images, it's not seeing something finicky or something bug that, because in the older days of 2016, this was one of the main headaches that you have. Like, you will never know if your images of your data is loading correctly and load of this. And the FastAI has this kind of option. You can kind of like see what is happening like this. And you can see like the labels of the images. They have like this vocab for this. This vocab to be the name of the classes, which are the label here is C. Background, signal is here. So it is properly load the images and already build the targets for me. I don't have to worry about nothing. So this is really, really great. And we can see the number of classes that we have like to classify. It says that it has 2 classes. What are the names of these classes? In my case, it was background and signal. This is come from the name of the folders. You can change it, you'll see that will be changed like this. And we can check like one batch. One batch, as I say, like, it will be random. It will take like 64 in my case here, 64 images from all my data set. It is combined in a batch, in a bunch, and this will be fed into the neural net. And the neural net will take like these 64 images, compute the gradient, go to the next learning step, and make it again. Once we finish all the batches, we have like, because we have like 5,000 images that we generate. Once we pass through all the images, all the 5,000 in batches like this, we finish one epoch. Okay, and this is like, okay, the batch will feed this directly, and once you finish everything, you finish one epoch. Go to the next epoch, do it again, and do it again. This is the main kind of ethos for training neural networks.
Question.
Yes.
Just to clarify, so the 64 images correspond to 64 events that are in one batch. 64.
Not 64 signal events. 64 images that can be 20 backgrounds, 44 signals. It always shuffle randomly.
So these 64 images, some have signals,
some have noise. Yes, exactly.
Okay, so and this is the learning process still of your neural
Yeah.
network, right?
Yeah.
But you're feeding all these images, and you are saying at some point that these ones are signals and these ones are not.
Yeah.
So you are distinguishing.
Yes, I mean
right?
distinguishing.
Okay. And then you do repeat this with, you said 5,000 images or
yes.
something like that.
I ended up all the images, and we have like, because every time when I feed like this 64, I compute the gradient, and I store like the value of the gradient like this. And I kind of like, I put 64, and my gradient descent go a little bit of the step, and I put more 64, go a little bit, and I'm computing this. All this gradient like this, and at the end of the epoch, we'll take all of these gradients and we'll average this, and we'll go one big step on the loss. We're going to do this. Okay.
Just to
yeah,
make it completely clear to me. So of all these images you're feeding, say half have signals and half don't.
Yes.
Doesn't, okay.
Yeah, I mean, not always the time I have to have signal, because this is like, we put like some shuffling. We are always random, and if the full data set, it has half of signal and half of image, it will be okay. Okay. But if the data set, the full data set, let's say like we have 1,000 signal images and 5,000 background, this will be not so okay. This will be like, we have like this imbalanced thing.
And images with signals are putting noise, of course.
Yes,
right?
exactly.
And different levels of noise.
Different levels of noise and different, all of this account.
Right. And,
I think that someone tried to enter on the lecture, and we'll see this. So I think that you have to allow. I don't know. I cannot allow for him.
Already done.
Okay.
It was
Okay.
already.
Yeah, I was complaining because it was like occupy my screen. But okay. So what we have here, we have the batches. We have all of this. However, in some GPUs, these batches cannot fit. I mean, we have 64 images, but the images are quite big. They have like 512 by 512 pixels. So these occupy a lot of my image. And I will not be able to train it. So I need to balance this. I need like to resize this, okay? We can delete our data and build it again. I mean, just remember that's like empty your GPU memory, because if you not do this, you like keeping your GPU always busy, and you have like some really strange error, like could GPU memory overflow or something like this. Just like try to empty your cache if you have something loaded like this, and create a new one that now we pass a smaller size like this. They say like, okay, instead of using this, use the same batch, use the same thing, but just resize the image, just like to fit in my GPU, and I can finally train like this. There is another trick that I'm going to show, I think that tomorrow, that we also use this to save memory as well, and I can explain better tomorrow. So again, just check everything, and now we have like, yes, please. Yes. Yeah, you can do reduce your batch size, but it will become like a problem. Like if you have a bigger batch size, we can train faster because a better representative of the model. Yeah, we are losing information as well, but that will be how willing are you to lose information or on this. You always have to try to find this balance. I mean, you can test if you are like your accuracy get really bad on this, so it might be a good path to resize your image. You keep your original image and put a smaller batch. It's always try and error. It's always like this. So for some problems, you can reduce the image, like for jet classification, for image jet classification, because you can have like a 4x4 pixel and it will have a really good prediction model on this. You can still have like really good. But for other cases, like in the gravitational wave, you can hurt your performance by doing this. So you always have like to find, there is no recipe for everything. So you always have like to find by yourself, depend on your problem, depend on things that you are doing. It will be. Luckily, we are going to buy new GPUs that have like lots of memory, so this will be like a problem. Yeah, that will be a problem of a past. So we can move on this. But if I try to do this by yourself on your computer on a laptop, I always try to balance this, like. And we can also check like what are kind of a normalization or what a kind of funny thing that FastAI is doing with the images, because what FastAI can do in the images, we can always like keep it tracking. Like just have to check if everything is fine, and we can use some transformations or some other normalization scheme. You always have this kind of a control like this. So another thing that's really important, I mean, that's make lots of difference, and this is still on debate on the machine learning community, is the normalization scheme. Because what the things that's like a neural net like to do is just like the neural net doesn't know this is an image. It only knows it's a matrix that has some fun numbers, and some really fun numbers is for one class and other fun numbers is for another class. This is all the things that can do. And he'll try to separate as best as possible on this. And depending on the way that you normalize these fun numbers, these matrices, it will make or break it. It will make really good results or really bad results like this. So what the neural net likes to work is numbers which has the mean value of 0 and the standard variation, the STD of 1. I mean, this STD take out of context is really troublesome, but the standard deviation like this. And people say that's like, okay, this can be applied for some cases, but not all the time. For some other kind of images, maybe the normalization scheme can be different and can be improve your performance. And there are these people from ImageNet, there's this ImageNet competition that has like I think that's 25 millions of images, belongs to 1,000 classes, and every year they runs, and the algorithms are became like really crazy stuff that people who run these kind of competitions, and they have lots and lots of good models. You can download it there. You can, as a matter of fact, we're going to use one of their models. And we can download even like this kind of like stats. That's like they have all of these images, and they build like these statistical deviations and all of this. And yes, for 2018, this kind of a normalization scheme that the people are using gave them like 99% of accuracy in some classification problems like this. And we can also pass this to the FastAI and say like, okay, take these images and normalize as this scheme, like this ImageNet, like this. And just to see. You see here this funny image. I mean, no worries. This is just like an artifact created by for the matplotlib. Like it even like warning me that's like, okay, we are like clipping the images of this, but this is not the image that are fed to the neural network. This is just like some sort of like approximation thing, so just make a show. So what they're showing me, that's like for this image in particular, we are feeding, these are like the most important features, like they has the highest value of on this normalization scheme. And we can have a look at the numbers. We can have like these are like, this will be what the neural network will see on my training, like this kind of a vector like this. And we can see what the FastAI is doing like this in each batch, what they are trying to look at this. So we already like, can I have like a little bit more time? So we are like past halfway done. So we are going to see. Another thing it is like, remember in the first lecture that we have like, we give this image for my flatmate to the neural net to predict it was a cat because I didn't take into account the rotations and everything like this. So if we have very few examples, like I was discussing with Carlos, like if you have like only 1,000 images for some rare events, like for some classes, what can I do to generate more of these images? What can I do like to make my neural net take into account like different kind of positions or different kind of thing? This is called data augmentation. We can take one image, and during my training phase, every time we need to load that images, it will not give the same image as it is. It will rotate a little bit, it will flip it, I mean, we can take into account all of this variation. And by doing this kind of data augmentation, what I'm doing is essentially like try to make the neural network take into account these predictions, and at the same time, I'm kind of like generating more synthetic data by using this kind of thing. Because even this is slightly rotation or some tilting or some different on the brightness or something like this, it might take into account for the neural net. It can say like, okay, this is a new data for me. This is a new image. Question?
Yeah, I'm thinking.
Yeah. Yes.
But I understand this with the dog example. It's very clear. You rotate, it's still a dog. It's just rotated. But if you have like one of these images to represent the gravitational wave event, it may be, well, then you wouldn't rotate, but you said you change the brightness or something.
Yeah.
But actually, that could correspond to a different event with slightly different parameters.
Exactly.
Right?
Exactly.
So
I'm kind of like building a new simulation inside the training phase.
Right, but it's not exactly the same dog.
Yes, exactly.
So it's a bit trickier.
Yes, it's really, really tricky. You have like to think really good about this, because depending on the way that you impose, you give your new augmentation, you give this, you can create a new example, but you have the label for that same example. Yeah. You are not taking.
If your goal is just to identify that there is an event, that's fine. But
if
it's parameter estimation.
Yes. For parameter, this is a completely different animal. This is like a really, really different animal. And we can feed this. I mean, we can take like one image and create like 4 different kinds of images like this. Of course, these are the 2 images, but depending on the way, you can create infinite number of images out of this, because these are discrete transformation. I'm just like flipping, changing, I'm just doing this. But we can put continuous transformations. Like here is a example of continuous transformation. These transformations are really interesting because what I'm saying here, this reminded me of my time in China, because I used to work with satellite images as well. And I cannot comment any more thing beyond this. Yes, it's true. I mean, I cannot like. So what one problem that we have to take into account, it was like, because again, Earth is round, okay, it's not like flat, and depend on the height of the satellite, we have this kind of a warp dimensions of this kind of thing, and we have to take into account this kind of distortions on the images. And we implement this kind of like a warped on the data set. And this makes like a really good predictions of the models like this. They take into account all of these kind of different things. And also by doing this kind of a transformation, we also take into account some like distortions on signals, some of this. So yes, it's really convenient. We can pass this argument here to the data loader, which called the batch transformation, and we can pass the augmentation transform. In that case, I pass the augmentation transform. It has like some basic default options, which are really good, which is like flip horizontally or flip vertically, tilt, or do some brightness or do something. You can always pass this. You can pass like the default and pass the default. And I'm just asked to change the dimension of the image to do this. And you can also pass like random cropping or put noise, or you can do really, really crazy things on this kind of thing. And you see here, it's doing this kind of transformation, okay? Yes, you have to think about it because we have a time dependency here. We always have like a increase in time from left to right and increase in frequency from bottom to top, like this. You always have like to thinking about this. I'm just put this because it's just for demonstration, but when you build your model, taking care into account of this kind of what kind of types of transformation that you are doing with your data that can influence on your final predictions. For classification is okay, but for try to predict chirp mass, try to predict distances, this makes huge difference for us. Okay. So again, we can check batches, we can check everything, and lo and behold, we already have like passed the data phase. What we can concentrate now, 5 more minutes, is the learning, the building the model by itself. I will build the same kind of model that we built for classify cats and dogs using the HasNet34, like this. And we can use this class of function called the CNN learn. This is convolutional neural network learning. The main things that you have to pass is the data loaders, the base architecture, and if I want to pass the loss function or any other parameter that I want, I can pass right here. So we create this here, and we can check what we create with the learn.summary. It will show you if it doesn't have any bug, if it doesn't have anything that you have to do this, and it show the dimensions and what each layer, what they're doing. Here we have like the input, the convolutional 2D. It will receive 64 images and convert it to each image in a new images of 64 channels by 64 pixels and 64 pixels. And we have this table here, is called the trainable. The trainable, it signalizes me if this layer, if this convolutional layer, during my training phase, it will change or not the weights and bias, like this. It's set to false because we are loading already trained model, already like a very, very well trained model in the ImageNet. This HasNet34, it's already trained. It was trained like for crazy with people using Amazon, and I don't need to train it again. I can just like pass this, and you see here, like it's quite deep neural network, as you can see, and to show you the total number of parameters. Remember when I said that's like for simple parameters, it's okay to compute the gradient. Try to compute the gradient with 21 million parameters. Try to do this, okay? However, you don't need to train in the 21 millions. We are going to train only in 545,000 parameters. We are going to only train the last layers, the classification layer that call it, which are going to, it usually say like the head of the parameter. Everything besides the last layer, it will remain freezed. It will not be touched by my gradient descent. Only the last layer that will be touched. This is called the transfer learning, and we are going to explore a little bit more tomorrow. So we can pass this. I'm not going to explore a little bit more of the cross entropy laws, but you can check these documentations. They're really, really good. And we can see the optimizer, also the algorithm optimizer that we're going to use. By default is the Adam algorithm, which is a modified version of this like yellow one, which is really, really fast. And you can try to use other ones. You can try to use stochastic gradient descent, momentum, or any other fun. You can even build your optimizer, your own optimizer for your own data, and you can train on this. You can just like feed the function, and FastAI will handle for you. Okay? So remember that I said that's like, okay, we have the batch size and we have the learning rate. A really good start is a halfway done job. Okay, if we find a really good learning rate that can have like really good steps that we can go towards the local minimum or luckily the global minimum as fast as possible, it will be great for us. FastAI can give us this kind of information like this learning rate defined. As I said before, we could choose a value here on the valley, but think like this, think like we are rolling a ball over some hills or something, and depending on the position that you put this ball, it will give like really good results. I'm not going to put the ball on the lower side here because the ball will just like will be there and might be it's not a good place to be. I will put the ball on the position where it's like more steeper, because when it's more steeper, it will gain a lot of momentum, and it might be lucky to find some really good minimum value of this. Think like about this kind of thing, and give this the learning rate. We are going to use not a fixed learning rate. We are going to change over time. We are going to change during the training this learning rate to avoid falling in some local minimums that are not good, and to accelerate our training as well. So all of this, we give the learning rate, you give all of this, and we train for only 7 epochs. If you see papers from 2016, 2015, you see people put like 200 epochs, 500 epochs, 1,000. I even saw one paper that's like a guy put like 25,000 epochs like this, and he even find a really good results like this. This is like hours and hours on our GPU, but here we put like only 7, and just look at this. We got 90% of accuracy, and that's like this is really, really good with only 7 epochs like this. Classify signals on this. I mean, just try to do this with TensorFlow with a fixed learning rate, just for giggles, just like this. And this is really, really powerful. So we can check how our learning rate evolves over time, and the momentum as well. The momentum is like another parameter that you like how fast your learning rate will grow or shrink like this. And we can check some of the results here. So in the top side, it is what the neural net predicted. In the bottom is the ground truth. And these are the images that we are predicting this. It's saying that like it's predicting the image is a background, and this right, it is a background. Yes. Yes, exactly. And even this harder one, you see, I mean, look at the background. Okay, I mean, it has some features, but even the harder one is getting as well. So this is a really good sign, because we are not only correctly predict on the easiest one, but we are also get really good prediction on the hardest one. Yeah.
I thought that it would give a probability for each image to be.
Yeah.
So when you say matches, you mean the probability is superior to 50%, or what do you mean?
I can show to you here the probability here. It will give like, when I ask for the predictions, it will give like the class, the number of the class, and the probability of that class was predicted.
Right.
It was this kind of thing.
So when do you claim that, say, it's a signal? Is it if the
Yeah.
probability is about 50% of being a signal?
In here, my case in fast AI, I defined the threshold to be above 90%. 90%. I can lower my threshold. I can lower like 7%. I can lower like this. I can still like. We have this flexibility. So, and we can check where we got. I mean, we fail here.
Sorry,
Yeah.
I'm curious about
Yes,
that.
please.
So you require the threshold to be 90%.
Yeah.
And then you get a 90% agreement, right? So
Yeah.
if you put your threshold to be 99%, what would be the agreement rate?
The agreement will be 99%, but I will have smaller and smaller samples that could pass this threshold like this, because this is in the training. But once I get like a set this threshold and go to the real data, it will be, if I put like a very high threshold for this, I mean, I will have like a very good prediction, certainty, 99% of certainty of my prediction. But
you can
not
only claim detection in a few.
In a
right?
few examples like this. I mean, you can set high this. I mean, you can tolerate somewhere. Okay. And we can see also where we fail. See here that it gives like it predicted that was a background, but in truth was a signal. With the loss, I mean, my loss cost, it is really high. Remember, I want this to be as close as possible to zero. Okay. So we can see here that the loss is high, and the probability that predicted that was a background is a 98%. So it's saying to me that he's really, really sure that that image is a background, but it isn't. So, and you see the common features that is like this is always trying to predict that there are backgrounds images, but they have signal. But these images, we are in a region that the signal to noise ratio that we generate from our data set is really, really small. It's really we are like, yes.
And I have a question precisely about that. So there should be a threshold on the signal to
Noise
noise
ratio.
ratio.
Yes.
Where
Yes,
it's
exactly.
reliable. So
Yeah.
it would be nice to know what is
Yeah,
that.
we can take this into account. Yes, and we take this into account, and you can even like estimate the signal to noise ratio threshold for the neural network as well. We can even build this kind of estimation.
Right.
From
Right.
this.
And it would be one, right?
Yeah.
At least we did.
Yeah.
Osvaldo is online.
We will talk about that in the
Yes.
other
Yes. Osvaldo is talking.
Yeah. Guys, could you try to speak a bit louder and closer to the microphone?
We were talking about the signal to noise ratio, but we were just discussing that Osvaldo will talk about this in the afternoon. And because Carlos was asking what is like the threshold SNR that could be. And we're discussing. Osvaldo, yes, please.
Yeah, I'm going to cover that a bit. So, yeah.
Yes.
So we can postpone the discussion until the afternoon because it needs to happen.
Yeah.
So yes, this is the last part. I promise. I mean, we are already one, and so how can we do better? We got 9%, but we can do better. We can always like get good on this. So one thing to do is just like, okay, we have we trained the model. We only trained the last layers of the model. All the layers before it was trained for some sort of a classification that was not for gravitational waves. So what happened if we unfreeze all of this, get a new learning rate? Okay, we get like a smaller one on the steeper one, and train it again. And yes, we got close to 92% of accuracy. So you can go crazy. We can do even better. We can like try to train it for more epochs, change the batch, and you can go do this. But we are reaching to a point that we are chasing zeros. Chasing zeros, that's like it will saturate. It will be like a 92.00009. So it might not worth the time spent or the energy. And think about the environment, because these GPUs generate a lot of heat and consume a lot of energy. I like it because during the winter, it is my heater. So it do this. And yes, but the thing is, Yeah, I mean, you can ask for the environment, but the Brazilian government is destroying all of this, so we are doomed anyway. And you can train for longer epochs and do more of crazy stuff. But it will always reach a point that is like it are chasing zeros and it's not worth anymore to do this. So you might stop on this or try to use other models or deeper models on this.
So
yes.
you're talking about an asymptotic value of about 92%.
Yeah.
Right?
In this case.
In this case. But do you think that changing the architecture, say, could improve that?
Yeah.
In principle.
Yes, in principle, I mean, you can like go deeper, go wider, go crazy. Yeah. You can test if you fit your GPU. You have like to resize and do the patch. But yes, you can test. I mean, I test with a HasNet 50 and I get like 92% of it. So sometimes it's the best is the smallest one. So yeah, have a question? No? Okay. So yes, you can also modify your HasNet. It was one case that we did. We didn't use a HasNet from the shelf. We modify some layers. We put like some really nice tricks, and you can get even better accuracy. You can modify your loss. If you change your loss as well, you get like different predictions. That's like the good thing. FastAI allows me to test this kind of crazy stuff, effortless. I don't need to implement from the ground and like try to do this. It's just like, okay, I see this paper that has this crazy. It was one thing that not enough, like Osvaldo say, oh, I see a paper that they modify with this layer and do this. And can you do this in FastAI? And say, build a model, feed this, and just run, and we can do this. This is like the beauty of the FastAI. You don't have to worry anything about this. You just like give the data, give whatever you want, and he will figure out for yourself. Okay, and I think that we can end up here. I mean, I tested in some real signals that we have, and we have like the predictions. Some ones they predict like really stronger, like 96% of prediction for this event here. These are all events, but other ones it fails miserably. Like here predicts like 93% that was a background and wasn't truth enough. And here I lowered the threshold to predict like 60% that was a signal, and we got this. And when we see when it fails, it always fails like in this kind of a situation, that like the signal to noise ratio is smaller and smaller. Or situation that is like not a binary black hole, but is a neutron star, or some situation that there was not trained for it. Black holes or things that are so. And also because the model itself, it only takes into account if it's a signal or not a signal. I'm not giving enough freedom for the model. If I put like a new class that is okay, signal, background, and slightly signal. So if you put, I'm 100% sure if you put these kind of things in the slightly signal class. So we all have like to think about, allow some freedom as well to the. Yes. Yes, exactly. And the things that could be interesting for us. Okay. And yes, I asked for 10 minutes and end up with half an hour. So I think that's all for today. Okay.
Okay. Thank you very much, Philippe, about this lecture. We are exactly at 1 o'clock.
Yeah.
So I think I don't know if we would have time for a quick question if people have